Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is part of the great stuff. This is the AAS Journal Author Series. And I am delighted to have Roberta Tripodi with us today. Hello, Roberta.
Hi, hello Frank, hello everyone. It's great to be here. Thank you, Frank, for inviting me.
Well, it's very nice you're going to talk about this very awesome article, which we'll get to shortly. And let's see, it's around December 19th of 2025
Yeah.
that we record this. And Roberta, what's your geolocation? Where are you at?
So I'm in Rome actually, because this is where I work. But
Mhm.
actually, tomorrow I will go back to my hometown in Calabria, in the south of Italy.
Oh, very cool. Very nice.
Yeah,
Let's see. And We're coming up on the winter solstice and the holiday season.
yeah.
How is the winter in Italy? Do you get snow in Rome?
So, well, actually, my precise location is Frascati, which is a hill outside Rome, slightly outside Rome. So here can be pretty cold, and actually, it snows during
Oh, okay.
winter. I think that in a couple of weeks, probably we'll have some snow. So while Rome is like warmer a little bit, but here in Frascati is pretty cold. Yeah. How
Okay.
about you?
So I'm in Phoenix.
Okay.
And Our winters are pretty gentle, I will say.
Oh, lucky.
We'll maybe go down to, let's see if I do this quickly. We'll get down to maybe about, 10 C or so,
Yeah.
about 40 F in the early mornings, and then it will warm up to somewhere in the mid 70s during the 70 Fs in the day, or quickly do that, maybe about 20, 25 C. So yeah, it's very pleasant in the daytime in Phoenix, and that's why we get all the snowbirds coming down from Canada for the winter.
Okay.
So it's
Okay. So
very pleasant in
pretty.
the winter, but we do pay the price for it in the summer.
Ah, you see. So it's basically the same in Calabria, you know? We
Yeah.
have, yeah, very quiet winter, but then in the summer it goes like 30,
Blast.
40 degrees. Yeah.
Yeah. Very good. Very cool. Very cool. All righty. And Roberta, what do you like to do for research?
So, well, I'm a early research career. So my research is currently pretty brief, but I got my PhD basically one year and a half ago, and I started working. Thank you. I started working on AGN, so active galactic nuclei. I'm very passionate about them. I really like these black holes in the middle of the galaxy that are messing around, especially at high redshift.
Okay.
So I and specifically, since now high redshift is basically even redshift 20 and so on, specifically, I work at redshift higher than 5, 6,
Okay.
and beyond. So AGN and also quasars during my PhD. And then in my postdoc, I moved towards little red dots.
Okay.
And now even Lyman alpha emitters, so normal galaxies. So yeah, yeah, normal. Yeah.
Little
So
red
what
dots
quite
and
broad
all.
interest. Yeah.
Very cool. Very cool. And that is going to bring us very naturally to this very awesome APJ letter. It is
Thank
open
you.
access. It's the open access era, people. You can go grab a copy for free. Go get one.
Sure.
A deep dive down the broadline region. Permitted O1, calcium 2, and iron 2 emission in the active galactic nucleus little red dot at Z equal 5.3. And Roberta, take us away.
Thank you very much. So yeah, there are pretty many, let's say, acronyms and names to be defined, maybe for the one that are not really in the field. But let's start just from like our collaborators, because I
Mhm.
didn't do this work alone, but I was followed by many experienced people, like for instance Marusha Bradach, which was my first advisor during my first year of postdoc, and
Okay.
also Francesco De Eugenio, who is a great guy. I love collaborating with him. And also many people, the following ones in the Canucks collaborations,
Ah.
and also led by Chris Willott, yeah, and
Hmm.
also some other external people like Alessandro Marconi and Bianca Moreschini, who helped
Hmm.
us in the modeling of
Ah.
the theoretical framework of this article. And also, I was supported by Laura Penterici, who is my current advisor in Rome.
Ah,
Yeah,
very cool.
also, yeah, she helped a lot, along with all the other, of course, co-authors of this paper.
Yeah,
But
it's
now
great. Yeah.
maybe, yeah, we can focus on the science now. So let's
Sure.
talk.
Let's
Let's
go.
talk. Yeah, let's talk a little bit about this interesting new population, the literate dots.
Hmm.
So just a heads up on this peculiar population. This was discovered by JWST in 2000, like 2 years ago, basically 3 years ago, very recent,
Uh-huh.
very interesting because we didn't know this kind of galaxies hosting this AGN, a redshift 5 and above, could exist
Uh-huh.
in the universe. And they are peculiar because they are very compact and they show a pretty peculiar spectrum, which we will go in a few moments.
Uh-huh.
And of course, in the last 3 years now, we have more than hundreds of publications about this population. So
Indeed.
it's pretty interesting. And we focused on this specifically, LRD Redshift 5.3, because he has, apart from the normal weird stuff that is involved in literate dots, he has also some interesting diagnostic that help us to access the broadline region inside the
Nice.
AGN, which is
Okay.
usually quite hard. So let's go
Yes.
and talk about the broadline region. As you probably know, this is a very compact region at the center of the galaxy surrounding the supermassive black hole in the center. And
Hmm.
of course, from the broadline region, we have access to the different emission lines. The more popular ones are the Balmer lines, H alpha,
Hmm.
H beta, H gamma, and so on. And
Yep.
these are important because we can derive the black hole properties.
Yes.
Okay. But the BLR is also interesting in itself because we can study the properties of the gas also in the BLR.
Mm-hmm.
And this we do with different kind of diagnosis, like magnesium 2, carbon 4, iron, oxygen, calcium, and also other kind of lines.
Mm-hmm.
And specifically in this paper, we focus on iron, oxygen, and calcium because these are the diagnostics that we detect in this specific object. So iron is pretty important, both in high redshift and in local AGN, because it's the major coolant of the BLR.
Yes.
And in principle, if you have observations that are deep enough, and also with higher spectral resolution, you can really resolve all the iron structure
Cool.
along the spectrum.
Cool.
And then you can get you can really understand the distribution, the spatial distribution of the BLR and also the mechanism of excitation of the BLR. So iron is really fundamental.
Yeah.
Unfortunately, at high redshift, let's say redshift higher than 3, 4, iron is pretty difficult to detect because it's mostly because of our limitations for the instruments that we use.
Okay.
Okay, if we could go infinite deep and with infinite resolution, of course, we could detect iron even at a redshift, I don't know, 10, 20. But of course, we
Right.
have the instrumentation that we have. But with WST, which is a great instrument, basically it's the most powerful eye that we have in the universe, in the space right now. We
Uh-huh. Yeah.
really we be able to detect the iron in a high redshift object like another LRD, which is able to 2744, a redshift 4.43, 47, sorry, published by Labbe 2024, and
Yeah.
also Kuiper's LRD at redshift 9. So even at redshift 10, we could
Wow.
have this detection, yeah, of the iron, specifically in the ultraviolet. But
Okay.
you have to
Yep.
imagine that the iron is really, there are so many iron lines that they made up a pseudo continuum, basically. So
Okay.
you can detect it from the UV to the optical. But
Okay.
this specifically was in the UV because they were pretty bright in the UV.
Right.
So, and actually, even though we detected these lines in the UV, there is a general population study by Trefoloni 2025
Mm-hmm.
who basically found that actually optical iron line are not so common in AGN
Yeah.
at high redshift,
Mm-hmm.
possibly due to their poor metallicity in the BLR. But
Yeah.
still, we are detecting some iron lines, both in the optical and the UV, and mostly in little dots. So maybe little dots, even though they are AGN, maybe they have some pretty peculiar properties that can distinguish them a little bit with the normal population of AGN.
Okay.
And since iron, though, is very difficult to study because of the many transition, because of our limited spectral resolution and sensitivity, we usually also adopt complementary diagnostics.
Okay.
And this leads us to the oxygen one, the calcium two, which really in this paper also specifically are really the key to really understand the BLR properties.
Okay.
And so yeah, also here a little bit, let's say, of history. So these are very old lines in some sense. So they were studied till when I wasn't even born. So in the nine.
That definitely makes
So
them old.
yeah, exactly. So even from the 80s, they were studied, of course, in the local universe mainly. So really Redshift Zero Galaxy, and
Uh-huh.
they already studied both observationally and theoretically. So they also developed, like for instance, Matsuoka 2007, 2008, they developed a photoionization model to explain the iron and the oxygen and calcium
Yep.
emissions in the BLR.
Uh-huh.
And specifically, what I found really nice is that you use different transition of the oxygen. You use the ratio between them to access the properties. So it's really a I don't know, task force or like a combination of all these group of lines. It's not like one line playing alone, but it's the combination of all of them.
I'm with
And same thing for the calcium, because you have a triplet, so you also
you.
compute the ratio between these calcium triplet, and based on what you get, we will see it in a moment. You determine different properties of the
Properties.
BLR.
Yep.
Yeah. And now this brings us to our specific object,
Okay.
which we called it BZ5.3
Hmm.
because it's an LRD that we found behind the bullet cluster.
Yes.
So we were pretty lucky because this means that this bullet cluster um, object is also magnified with a magnification of 3.7, so let's
Cool.
say 4.
Hmm.
And probably this is also why we can detect these many emission lines arising from the BLR, which usually are hidden because of lack of sensitivity. So
Right.
maybe this could be an explanation. And we use, of course, JWST observations, near
Hmm.
spec for sure for the spectrum, but also
Yep.
photometry from NIRCam.
Mm.
And talking a little bit about the data, this bullet cluster is a newcomer in the Canucks collaboration
Okay.
because yeah, the Canucks collaboration is basically they are targeting 5 clusters. But now also we added the bullet cluster to them, so
Okay.
we have 6 of them. And of course, one of the main goal of the bullet cluster study was to study the dark matter distribution and whatever is interesting about the bullet cluster.
Mm.
But since LRDs are everywhere, we also detected this fancy guy behind the bullet cluster. And
Cool.
initially, BZ5.3 was selected using photometric data only through NIRCam.
Yeah.
And then we followed up with near spec prism spectroscopy.
Okay.
So we get the full spectrum, but with low resolution. But at least we can see all the spectral shape. So if we now go to figure 1, we can have a look.
Let's take a look at what it looks like. Okay.
Yeah.
Zoom in a little bit.
Okay.
We'll get the global.
Yeah. So here you have on top the 2D spectrum. So you see the wavelength as a function of the space, the spatial distribution. And then you have the spectra, so flux
Mhm.
versus wavelength. And then you have also some pretty cool images from NIRCam in very different filters. and it ends up with a RGB image on the bottom on the bottom right. Yeah,
I'm
exactly.
with you. Mm-hmm.
And if we focus on the spectrum specifically, we see why LRDs are so peculiar. You see, the black line is our LRD. The yellow one is just another one from comparison. We will talk about it later. But you see this pretty V-shape. So the spectra of LRD are really V-shaped.
Yes.
And the turning point is more or less 3,700, 800 angstrom. So they really have the turning point at the exactly same place, regardless of redshift.
Okay.
So this is also, yeah, so it's really a key feature of this whole population.
Okay, got it.
So yeah, so this is what makes LRD interesting, but specifically for this, you see a like thriving population of emission lines from Lyman alpha from the UV to the calcium triplet in the really redder optical.
Yes.
And of course, you have also high ionization lines in this object, like nitrogen 4, carbon 4, just blue word of Lyman alpha. And then we go to the iron feature near the magnesium 2. Yes. It's easy to see because I color it in blue. And then you have some optical diagnostics and optical lines like oxygen 2, neon 3, which is sensible to ionization and metallicity. Then you have the Balmer series, so H delta, H gamma, H beta, some iron features also there, the oxygen 3, and then some helium lines, blue wards and red wards of the H alpha, which is also pretty bright, cool. And as you see, also pretty broad. And that's why we thought that these LRD host are supermassive black hole in the center.
Good.
And then you have at the end of the optical the oxygen 1 8446 and the calcium triplets.
Very cool.
And so there is really plenty of information. Like for the sake of this paper, we focus just on these iron, oxygen, and calcium triplets. But we will follow up with another paper on this object, also studying all the other properties.
Well, we'll come back to
Spoiler.
that. We'll come back to that. Okay.
Yeah. And now if we go and have a look at the morphology, so really at the photometry, you see another key feature of LRD. So if you look at the filter 444W, which is the bluest one, you see that the shape of this LRD is pretty like PSF shape, so round. Yeah. Also, you can see it from the RGB image. It's really a little red dot. So pretty on point. But actually, when the resolution increases a little bit, so towards the bluer filters, so F090, F115, and 150, you see some also extended components. Yeah. Right? Yeah. Exactly. Exactly. We can also have a look at it we analyze the morphology of this object in the Appendix A. In case we want to have a look at it, there is a Gauss fit analysis. So basically, we fit all these filters either with a PSF only model or PSF plus another component. And what we can see is that for the reddest filters like F410 and F444, these are just PSF, so it's unresolved. While if we go bluer, then there is some resolved structure. So the best fit is central PSF plus an additional component. So you really see the host of this AGN basically. And this is pretty interesting because usually for like 70% of the study population of LRD, these LRDs are unresolved in all NIRCam filters. So you don't see the host galaxy. But for a lower percentage of the population, like 20, 30%, then you can see the host galaxy in the bluer filters. And we were lucky for BZ, in case of BZ 5.3, because we could see. this
Nice.
host galaxy, probably also because of the magnification in some sense, of
Yes, that
course.
helps. Yes.
Yeah,
Cool.
yeah. And now we can go back to the main paper, and
Hmm.
maybe we can have a look at, let's say, at the analysis, because as I mentioned before, yeah, this is the day we talked about the data, and
Yeah.
then
Yep.
we started analyzing that the
Mhm.
spectrum specifically. And so of course the first thing we wanted to do is to really check our LRD selection, computing the slopes in the UV and the optical,
Yep.
and we confirm that this object is an LRD, as we can also see by eye, of course, but
Good to
quantifying
be
these things for,
quantitative. Yes.
yeah, exactly, exactly. Otherwise,
Hmm.
no one is going to believe us. And then, as I told you, there are many emission lines, and
Yes.
specifically from the broad H alpha and the broad H beta, we could derive some black hole properties, which we mention here, and then we will talk about it in the follow-up paper. But basically, the black hole mass is of the order of 10 to the 8 solar masses,
Okay.
which is, let's say, pretty common at this redshift. It's not an incredible black hole, exactly. It's just
Right.
that when you pile up all the information together, then this object is interesting. But for the black hole itself, it's a very normal guy, let's say,
Yeah.
a
Yeah.
redshift 5.3. And also, as you see from the bolometric luminosity, is 10 to the 44,
Okay.
normal, completely normal AGN. So yeah, this is pretty nice. At least this was pretty simple, let's say.
In that sense, yes.
Exactly. And then, of course, we fitted the whole continuum and the emission line. In this paper, we report just the spectral fitting of the oxygen one in the UV, and the iron feature and the calcium triplets, and the oxygen
Yeah.
one in the optical.
Okay.
And specifically, I want to mention that the hardest part was to fit the oxygen one in the UV, so the one near the Lyman alpha,
Okay.
because I didn't know this before doing this study, but actually that oxygen one is actually a blend of two lines, the oxygen one and the silicon two. So I was at the
Okay.
first beginning, I was pretty
Well,
disappointed. Exactly. Oh my God, how I'm going to derive robust stuff from this. But also this blend was studied before in the literature.
oh,
So of course the work of the community in this case helped me a lot, and specifically in the low redshift universe.
cool.
So basically, you have this blend, which in our spectra is unresolved. So you have to fit one single Gaussian, you get the flux of the blend, and then you need to assume a ratio between oxygen 1 and silicon 2 to
Okay.
get the flux of one of the other, or the
Right.
other element.
Right. I'm with you. Mhm.
Yeah, so specifically in the literature, this blend was studied, as I said, in the lower redshift universe, where you can also resolve the blend. And what they found in specifically Laur 1997, I was 1 year old. They, sorry, they basically found that this flux ratio between the oxygen one and the silicon two is of the order of 50%.
Okay. Okay.
Yeah, so it's split at half and half, let's say, on average. But then you can go even to the silicon 2 to dominate the blend in some specific cases. And specifically is when the Lyman beta fluorescence don't excite a lot the oxygen one. So the
Right.
silicon 2 basically dominates.
Okay.
But it can also happen the other way around. So basically, the silicon 2 contribution is 30%, 20%, and the oxygen one is dominating. So you can have different behaviors, but on average, it's, let's say, 56%.
Okay.
Yeah.
I'm with
And
you.
also, yeah, exactly.
Okay.
So yeah, you see, these are studies of objects between redshift 0 and 1.1. So of course, we tend to extrapolate these results into the high redshift universe. But since the physics behind the excitation of this element in principle doesn't change, then I think it's totally
Fair
fine
enough. Fair
to,
enough.
to do
Okay.
this kind of work.
Okay.
So yeah, this is about the origin of this blend, exactly. And
Good.
then if we go to figure 2, we can have a look at the blend.
Yeah, let's take a look
Speci-
at that. So we get a
yeah,
good.
specifically left panel, you
Mm-hmm.
see basically this oxygen 1 1304, and basically, yeah, basically they are pretty attached, pretty close together. Indeed, I didn't even draw two lines because otherwise, basically they superimpose. So it's difficult to see. So you have to imagine that within these 3 pixels, there are two emission lines.
Okay.
But still, this detection is in any case significant because we have a signal to noise more than 6, so
Good.
it's
Okay.
still detected. Yeah, the blend. And as you see now on the right, there is another zoom in into the other oxygen 1, which is
Uh-huh.
even more significantly detected, basically signal to noise 10. And as you see, with respect to the calcium triplets line, the
Mhm.
oxygen one is pretty broad.
Yeah.
It's
Yeah.
pretty broad. And we will talk in a second about why oxygen 1 is broad. And well, actually, we can talk it even now. So why not?
Okay.
So basically, the oxygen 1, what I found really surprising when I studied this line the first time is that oxygen 1 is always found to be broad. There is no narrow component for the oxygen 1.
Okay.
So in principle, you expect a line to have 2 components: the narrow one, which arises either from the narrow area region or from the host galaxy itself,
Okay.
and then the broad component, which arises from the BR. But
Yeah.
the oxygen 18446 has just a broad component, even in the low redshift AGNs, in which we
Okay.
can resolve the galaxy. So in principle, if there was one, we could detect it, but
Right.
no. So
Okay.
it's just broad. So this kind of oxygen one is really arising from the broad line region of the
Yes.
AGN.
Yeah.
And that's why these are key diagnostic for inferring the properties of the BLR.
Yes. Okay.
Yeah,
Cool. I'm with you.
exactly. And
I'm
in
with you.
principle, if you have the spectral resolution to resolve also the other lines, like the calcium triplets and also the other oxygen one, in principle, you can see also where specifically these lines arises.
Right.
So unfortunately, yes, the calcium triplets are not resolved, are within the resolution of the instrument in this wavelength range. But for sure, what we can see is that the oxygen 1 and calcium arise from slightly different part of the BLR. So you
Mm-hmm.
have this kind of stratification of the
Right.
BLR,
Right.
right? So
Right. Right.
yeah, exactly.
Mm-hmm.
And
Mm-hmm.
this
Good to
was
read.
one of the main point of this paper. And then also after this paper came out, there were also other papers on LRDs talking about these BLR certifications also in other objects. So
Okay.
it's not really peculiar of this one, but
Good.
probably it's a properties of the population in general. Yeah,
Good.
yeah. Even in the local universe, because now we found also local analogs of little red dots. Yeah, so apparently they were really nearby, close, but we never looked at them. But yes, they have pretty much similar properties of the high redshift
Cool.
ones.
Good. Good.
Yeah, yeah.
Okay.
So
Very nice.
what's next? Sorry, I don't remember exactly all my paper by
Yeah, oh,
what's
believe me,
next.
I understand. Let's see. We got into some emission line measurements there.
Yeah, yeah. Maybe we
Uh,
can skip this part. This is, I mean, just fluxes, which we can have a look at the table 1, actually. So table 1
table one.
report
Yeah, yeah.
all the fluxes of
Mhm.
the emission line of interest.
Okay.
And specifically, I think what's
Okay.
more interesting, the full width of maximum of the oxygen 1, which was the only one we could resolve, as I told you. You see, it's basically 1,000 kilometers per second, so pretty broad.
Yeah.
Uh,
Pretty
these
cool.
donalized, yeah. And then also the equivalent width is pretty high.
Yeah.
And this tells us, I mean, the equivalent width of this line specifically help us in distinguishing the excitation mechanism of the gas in the BLR.
Uh-huh.
And let's say spoiler, this tells us the Lyman beta fluorescence is the main trigger of excitation for this object,
Cool.
followed by collisional excitations.
Yeah.
So the combination of these two is really the key. Yeah, the key for them. And as you see also, the oxygen 1 equivalent weight is basically comparable to the magnesium 2, which is also a strong line.
Yes.
So yeah, it's oxygen is pretty powerful, let's say.
Okay. Yes.
Yeah, in these objects specifically.
Okay.
And yeah, later on in the paper we tried to model also the iron 2 in the UV. This is usually done with templates, Westergaard templates, Suzuki templates. These are the most common ones because it's really hard also, given our spectral resolution, to really model all the features because you don't see them. Yeah. So you use these templates and you see whether the relative flux of all the iron 2 emission lines matches with what you see in your spectra. Okay. And this is actually what we see. I think it's figure 3, I would say.
Okay. Let's take a look at figure 3. This is the yes.
Figure 3, right panel, we have the iron in the UV, which is also blended with the magnesium 2. So you see, of course, in black, there is the observed spectrum. In blue, there is our fit. And in yellow, there is the template that we used to match our observation. And as you see, the template has these 2 bumps. The first one is to 2500 angstrom, more or less. And you have other iron features, let's say, that are near magnesium 2. You have, exactly. These other,
maybe this one,
Exactly. So this is just the template that we took without changing anything, just convolving with the resolution of the instrument, of course, and we scaled it and paired with the magnesium to emission line and the continuum as a power law. Yeah. But actually, if you try to play a little bit with the template, then you can have some nicer match with your spectrum. Because in principle, here, using this template without modifying it, I'm assuming that all the conditions of the gas that they assumed in their model are also the same for my object, which in principle is not true. In principle, it can be, but so if you just modify the relative ratio of the iron 2, which we do it in the appendix, then you find basically quite a perfect match. Just modifying a little bit the ratio. Yeah, we can also have a look at it.
Let's slide down. And, that's appendix 3. So these are alternative iron and magnesium.
Exactly, figure 6. Exactly.
Yep. Let's take a look at this one.
Yeah. Here, now you see that basically we recovered better the bump at 25. Both bumps basically. Now it's within 2 sigma basically. And I just altered one of the iron ratio. So in principle, you can what in principle you should do is to do a precise photoionization model.
There you go.
Then you do this, and then of course you can really model your spectrum precisely. Of course, not accounting just for the iron in the UV, but also the iron in the optical, along with all the other emission lines.
Yes.
Which actually we started doing in this work with the help of Alessandro Marconi and Bianca Moreschini, which I mentioned previously. So they helped us with their code OMRAN, which performs photoionization modeling, of course, with some assumptions. And we started trying to see whether and we started to see whether there are some combination of gas properties that can reproduce our spectrum. And like for this initial analysis, we just used some Balmer flux, and then of course the iron fluxes and magnesium fluxes that we have. And the result was, consistent with what we get from the template, but we can do better than that. And we will do it in our follow-up work about this object. Yeah.
Okay.
So this was just a first test, just to see whether we can trick the model a little bit to get, yeah.
Opening
Yeah,
shot. Opening shot.
yeah, yeah, exactly. So
Okay.
yeah,
Let's
and this
slide
is
back.
why, yeah, and this is why iron is difficult to model, as you see, because it's not iron itself. We have to take into account all the other emission lines and so
Correct.
on.
Yes.
Yeah.
Yep.
And
Yep.
if you go slightly below, basically in the section after the table 1, we started talking about this VLR stratification,
Mm-hmm.
which I mentioned before. Here we are going pretty much into some details because we are accounting for the difference that we see also in the iron itself from the UV to the optical. Because while you go bluer, while you go redder, sorry, you get a better resolution. And so basically the emission line we saw that the emission line in the optical were also narrower than the limit we can get from the UV. So
Yes.
basically we can start talking about whether this iron is really broad permitted or narrow forbidden lines.
Uh-huh.
This is
Uh-huh.
still an open question
Yes.
for this object in particular. But now there are also some other works on other LRD which are saying that these iron lines are probably just a forest of forbidden narrow iron lines.
Gotcha.
So
Mm-hmm.
maybe also ours, maybe also this could apply also for our object.
Yeah.
Maybe. And they also see that in the local analogs of the LRDs.
Mm-hmm.
And as you see, during, of course, scrolling down this section, we mentioned many different limits that we get for the full width of maximum of the lines. As you see in the optical, these are like less than 5,000.
5,000. Yeah.
Yeah, for the inconsistent line, and we measure them to be basically less than 2,000. So this is consistent with this picture, but still we don't have let's say, the detection of this full width of maximum. So difficult to draw really solid conclusions. But still, we have a starting point, and in principle,
Exactly.
we can go for higher resolution observation,
Very
even with WST, just using the gratings instead of the prism.
Oh, yeah. Mm-hmm.
Yeah, if we are able to get the data, which is not easy. Yeah, finger crossed. And then so this is of course the difference that we see between the optical and the UV. Of course, this is support the stratification of the BLR even within the iron, and specifically also if you compare the iron with the oxygen, which is at 1,000 kilometers per second, this is also further support. And the picture that basically is more not reliable, but let's say spread around the community, is that this iron this gas traced by the iron is at the interface between the BLR and the narrow line region.
Yes.
So it's really in the middle between them.
Okay.
Yeah,
Good.
which is pretty cool. Yeah.
Very nice. Yeah. Beautiful.
And then after talking about the certification, we talked about the excitation a little bit.
Mm-hmm.
So actually first I think about the dust continuum, but probably we can also skip it because, well, it's interesting, but it's also very uncertain in some sense because
Mm-hmm.
we compute the dust attenuation from the ratio of the oxygen line in the UV and optical.
Yes.
So given that we get a ratio that is very, very low, in principle, we expect 1. Because if you look at the Gottran diagram, you see that oxygen 1, 1304 and 8446 are produced with the same rate, let's say.
Right.
But we see a ratio which is 10%, so 0.1, 0.3, very, very low.
Mm-hmm.
And this cannot be, let's say, reconciled just with some other mechanisms. So for sure there is some dust there, which is attenuating a little bit.
Yeah.
But still, given that we don't know actually, which is also what is really the flux of the oxygen 1 because of the blend with silicon 2, then we have a full range of possible dust attenuation, which basically goes from 0.4 to 1 that we mentioned at the end of this section. And this, yes, so we have from mild dust attenuations to some high, let's say, dust attenuation. So yeah, 0.4, 1.4. And then, of course, after talking about dust attenuation, we also wonder what the origin of the UV continuum was. And just based on the UV slope, we said that this is totally consistent with the standard accretion disk. So AGN, basically AGN playing also its role in the UV.
Yes.
And then from the calcium triplets, let's say alone, we can say much because, as I told you before, we are limited by the resolution of the prism. But of course, these are useful when we compare them to the oxygen one and to the iron. So standing alone, we just can say that basically these, based on the ratio of these triplets, we can say that the gas is optically thick, which still, I mean, this still helps for our photoionization models. So it's still pretty the information, but it's limited to that. And thanks to all these lines, calcium, oxygen, and iron, then we can talk about the excitation mechanism.
What make them go.
Yeah, which is basically the core of this work. So as I told you, the ratio between the oxygen one transition is expected to be 1. So we see that this ratio is lower than we expect, and this is usually done. The main reason is because Lyman beta fluorescence is exciting this object. But in principle, there are also other processes that can help, let's say, which is recombination, collision excitation, and continuum fluorescence. But we can rule out some of them thanks to the other lines that we detect or also not detect. Because, from the equivalent width and of oxygen 184.46, which is pretty high, we saw them before, we can see that we can say that Lyman beta fluorescence and collision excitation are the main mechanisms. Of course, comparing with photoionization models. So of course. But then, given that we have some stringent upper limits on the oxygen 1, 7774 and 7990, which are also in the optical, then we can rule out some other processes. And in particular, the processes that we can rule out are recombination and continuum fluorescence. Because in principle, if these processes are also competing, then the flux of this line are higher, way higher. In principle, we should detect them, but we don't. So this is why we can rule out these. And actually, we can also rule out the continuum fluorescence thanks still to the equivalent width of our oxygen one in the optical. Because if continuum fluorescence was in place, then the equivalent width expected from models is very low, less than 1 angstrom, basically. But we have 24, so it's a factor 20 higher. So
Beautiful.
Here basically we can see the power of combining all these emission lines, because really we can really disentangle all these little processes, which in principle are entangled all together. And specifically when we also combine the equivalent width of oxygen 1 and the calcium ratios, we can also try to understand which is the ionization parameter of the gas and also the gas density in principle. So still comparing with the photoionization models with a pretty large grid of parameters, so of ionization parameter and hydrogen density, we saw that the ionization parameter in our gas is between -4 and -3.5.
Yes.
So it's pretty low. It's pretty low also for
Yeah.
being an AGN in some sense,
And
because what we saw from the recent WST results is that ionization parameter for AGN will also be as high as -2, -1.5, -1.
right.
So based on this standard modeling, we retrieve this low ionization. Of course, for the gas traced by calcium, oxygen, and iron, which can also be like the outer edge of the BLR. So
Okay.
in principle, can also be true that maybe that part is less ionized than the closer one from which Balmer lines came, for instance, or carbon 4 or nitrogen 4, the higher excitation
Right.
levels of this line. So,
Right.
so this is still pretty much consistent with our picture, let's say, of the BLR. But for sure, we will know more with our modeling with Alessandro Marconi e Bianca for this galaxy. So yeah,
Very good.
so stay tuned for that.
Very cool. Good. Good, good, good. Okay.
Yeah,
And then we just summarize away here. Okay, very good. Awesome.
yeah, yeah,
Very
yeah.
good. Roberta, I want to thank you so much for walking us through your very
Thank you.
awesome APJ letter. Very nice.
Thank you.
Yeah. Let's see. And well, you hinted at it more than once as we went through. And so let me phrase it this way. Where do you think we go from here, given the published article? Is there additional observations in the pipe that may be able to help? Are there other wavelengths that might be of interest? Is there additional theoretical modeling that could be done to help verify or refute some of these results? So where do we go from here?
Yeah, so thank you. So I don't want to repeat myself. Of course, we will do photoionization modeling, fine. But then there is much more too, because like in the last weeks, there were many articles about LRD, improving the modeling of the central engine, and
Okay.
also how we perform the spectral energy distribution fitting of these objects
Yeah.
for retrieving the stellar mass, metallicity, and other interesting properties. So
Okay.
what we are going to do next is to try testing these models also for our object
Okay.
to see whether we can refine our estimates for the galaxy properties of this object. Of
Yes.
course, we will ask and luckily we will get some higher resolution and deeper observation of
Right.
it. And our goal also as the Canucks collaboration is also to expand this study with
Ooh.
other
Yeah.
LRDs.
Yeah. Yeah.
Yeah, yeah, still in the cluster fields. We hope to see some also magnified ones, but also the normal ones are still
They're
acceptable.
fine too.
Yeah, we are very inclusive. So every LRD is nice, and of course, the bigger the population is, the better we can constrain all the modeling and the physical properties.
And the evolution,
Yeah,
right?
and the
Presumably there's
evolution.
some evolution going through. So yeah.
Yeah, yeah.
Hmm.
So yeah, this is our next steps.
Very cool. Well, it'll be very exciting to see over the next, well, given the compressed timescales, maybe weeks, months, or even couple of years as
Yeah,
this
yeah.
develops even more. So it'll be very cool to see. Very nice.
Thank you,
Beautiful.
thank you,
Beautiful. Beautiful work. Thank you, Roberta.
thank you very much.
And that
Yeah.
will do, everyone. And I hope this made your astronomy day just a little bit better. And we will see you on the next one. Bye bye.
Bye.